Okay, guys, this is the second lecture on deflections. Let me remind you first what we said before in the first lecture. I was explaining here the virtual work method. For example, if we are having any structure like this, any frame, due to the application of gravity and lateral loads, W and P, point N will move from its original position to another position N dash. Okay, such that I will have vertical displacement, horizontal displacement, and rotation. Okay, by the virtual work method, you can get one of these values at a time. Imagine that we want to get the vertical deflection. So I'm going to remove all of the loads, keep the same geometry of the frame, the same supporting condition, and I'm going to put a unit load. Now, this system is called the main system. I'm going to calculate the moment, the shear, and the normal force. And this system is called the unit load system, where we calculate the moment and the shear and the normal force due to this unit load at point N. And finally, by the virtual work method, we can say that the external work done due to the unit load and the deflections of the main system, which is Uy, is equal to the internal work due to the internal forces caused by the unit load system and the displacements caused by the main system. So we are multiplying M1, M naught, dl over EI, and we are integrating because the value of the bending moment is changing throughout the length. And the same thing for the shear, the same thing for the normal force. And we said that this means that the vertical deflection at point N is basically or constitutes of or consists of three components. One component is coming from the moment, and the other component is coming from the shear, and the third component is coming from the normal force. In the previous lecture, we applied this on trusses. And we said that in the trusses, I don't have moment and I don't have shear. Therefore, the vertical deflection will be equal to N1, N naught, L over EA. And instead of having integration, I will have summation because the normal force in the truss member is constant. It is not changing with the length. Therefore, the integration will change into summation. And we solved several problems or two problems on this application. Today we are going to talk about deflection of beams. Now, if I want to get the deflection of beams, I would say the same general equation, the vertical deflection at any point Uy equals to integral M1 M naught dl over EI. We are going to neglect the normal force component N1 N naught dl over EA because this is very less. It might be 0%. Already we might not have normal force in the first place, and also the magnitude of the deflections caused by the shear is very less. Maybe it constitutes 1%. So 99% is caused by the moment and the rotations associated with it. Therefore, in the deflections of the beams, we are going to use this equation. We cannot change this equation into summation because the bending moment changes from one location to another in the beam. Therefore, I will have to use the integration. Okay, now let me explain for you the applications for this method on the beams. Now, we said that the deflection will be integral M1 M naught dl over EI in beams. How can we do, or how can we solve for this integration? Case 1, if M1 and M naught are of the first degree diagrams, which means that M1 and M naught is linear. Imagine that I am having a diagram like this. This is M naught, and we are having another, or the corresponding diagram for M1 is like that. Okay? Now we are going to get the area of this diagram A naught and the area of this diagram A1. And then we are going to get the centroid of this area and get the corresponding ordinate here. So how are we going to get the centroid? We get the centroid from the centroid of well-common shapes or composite areas that we studied before in chapter 5 in 212. So corresponding to the centroid, we are going to get the ordinate. Let us say the ordinate is y1. Or we can determine the centroid of the other diagram M1 here, and we get the corresponding ordinate y naught. So the rule is saying that we can solve for this integration graphically. We don't have to go mathematical. We can say that integral M1 M naught dl over EI, that is equal to either that we take the area of this diagram and we get its centroid and get the corresponding ordinate from the other diagram, multiply them by each other, which is A naught y1 over EI, or vice versa. You can start by getting the area of M1 diagram, which is A1, get the location of its centroid and get the corresponding ordinate here. You can say here that this is A1 y naught over EI. Either that you can go the area of M naught and multiply by the corresponding ordinate to the centroid of M naught, or you can get the area of M1 and corresponding to its centroid you get the ordinate here y naught, and you multiply A1 by y naught over EI. Let us have examples. Now imagine that we are having, this is M naught diagram, it is negative and its value is A. This is L. The corresponding M1 diagram is a triangle like this. I want to integrate this rectangle on the triangle. So I'm going to say integral M1 M naught dl over EI equals. We can start by the area of this figure, and the centroid here is in the middle, of course, because this is a rectangle. The corresponding ordinate is b over 2. So you can say that the area of the first diagram AL multiplied by the corresponding ordinate from the other diagram b over 2. This diagram is negative and this diagram is negative. The product of two negative values is positive. Okay? Or you can say that I will start with the area of the triangle. So the area of the triangle is BL over 2. The centroid of the triangle is at 1/3 base. Then you are getting the corresponding ordinate to the centroid of the triangle, which is constant. It should be A as well. So these two results are the same. So either that you started from here or you started from there, you should be getting the same answer. Okay, another case, if this is a triangle and this is also a triangle. Okay, so what will be the integral in this case? Okay, now I will start by getting the area of M naught. This is M naught and this is M1. So I will say AL over 2. The centroid is here, and I want to get the respective ordinate. This distance is L over 3. So this remaining distance is 2 over 3L. We are saying that this distance over this distance is equal to the ordinate over B. So this value should be 2/3 of B. So this is multiplied by 2 over 3 of B, which means that, of course, you are integrating now negative on positive, يبقى the result will be negative. يبقى this is negative ABL over 3. Okay, let us have another two cases. If you are integrating a triangle like this on a triangle like that, this is M naught and this is M1, and we are integrating a trapezium on a triangle. So this is A, this is B, this is negative, and this is C. Let us see what we can do here. So integral M1 M naught dl over EI equals, I will start by the area of that one or the area of that one, it doesn't matter. Let me start with the area of M1 diagram. So it is BL over 2. Now this is negative and negative, يبقى the result should be positive. Where is the centroid? The centroid is here. It is at a distance of L over 3. So we want to get the respective ordinate. This is L over 3 and this is L. يبقى therefore this should be A over 3. يبقى the respective ordinate here multiplied by A over 3. So this is ABL over 6. طيب, how about this case? Now, if you wish to start with the area of this diagram, this is a trapezium, we don't know its centroid, okay? So we can divide this into a rectangle and a trapezium and a triangle. This is A, and this will be B minus A. We can integrate the rectangle on the triangle and the triangle on the triangle, and we add them together, okay? So if you want to get integral M1 M naught dl over EI, this will be equal to, let us integrate first the rectangle on the triangle. The rectangle, its area is AL. The centroid is here. The respective ordinate is in the middle. This distance is L over 2. يبقى this should be C over 2. Okay. The remaining triangle will be plus B minus A L over 2 multiplied by, the centroid here is at 1/3 base. So you want to get the respective ordinate. This distance is L over 3 and this distance is L. So L over 3 over L is equal to the ordinate over C. يبقى this value is C over 3. So this should be multiplied by C over 3. Okay. Another case, if we are having a trapezium integrated on a trapezium. imagine that we are having, this is A and this is B, this is M naught diagram, and here this is negative and this is negative as well, C and D, and this is M1 diagram. So as if I'm talking about a portion in the beam, we have to integrate all of the portions together. This is a portion of the beam where M naught diagram looks like that and the corresponding M1 looks like this. The ideal method is that I should get the location of the centroid of this trapezium and multiply the area of the trapezium, which is average base times height, multiplied by the respective ordinate to that. But maybe we don't want to go into this calculation because it will be a little bit lengthy. So I have to divide this into, as before, into a rectangle and a triangle. I will integrate the rectangle on the whole trapezium and the triangle on the whole trapezium and add them together to get the answer. Okay? So we have this part here. This is A and this is B minus A. So let us start. Integral M1 M naught dl over EI will be equal to the area of the rectangle. As long as this is linear and this is linear, we can start with any one of them, but I will start with this because I know the position of its centroid. So this is A multiplied by L. The centroid here is found in the middle. The respective ordinate will be the average because this distance is L over 2. This value should be C plus D over 2. Okay, this is C plus D over 2. The sign here is positive because I'm integrating a negative diagram on another negative diagram like this. Okay. Now for the triangle, we are going to get the position of the centroid and we want to get the respective ordinate. Okay. So the area of the triangle will be how much? This will be plus B minus A multiplied by L over 2 multiplied by this respective ordinate. Who can tell me how can we get that? Now, if we divided this into a rectangle and a triangle, you will find that this distance here is D. And this distance is basically how much? Because this is L over 3, this should be C minus D over 3 from similarity. As long as this distance here is L over 3, so you know that L over 3 over L should be this value over this value, which is C minus D. Therefore, this ordinate will be D plus C minus D over 3. So this will be C. This will be D plus C minus D over 3. Okay? If we want to integrate a trapezium on a trapezium, the result will be like that. Okay? So these are the cases as long as M node diagram is linear and M1 diagram is linear. What if the diagram M node is parabolic, is of the second degree? What should we do? Let us see. So we are having case 2, M node of the second degree and M1 of the first degree. In general, the curve of M1 can be like that, of M node can be like this. This is the shape of the bending moment diagram, and the corresponding moment diagram due to the unit load M1 is linear like this. Here, if you want to do the integration, there is no choice. You have to start with the area of the second degree diagram and multiply by the ordinate corresponding to the location of its centroid from M1 diagram. What does this mean? It means that I will have to determine the centroid, and from the centroid I will get this ordinate y1, and I have this area is A naught. So this means that the result here will be A naught multiplied by y1 over EI. Now you cannot go the other way around. You cannot take the area of this diagram and multiply by the ordinate corresponding to the centroid of M1 diagram. As long as this is of the second degree, you have to start by calculating the area of that one. Okay? This means that we have to remember the area and the centroid of some curved shapes that we studied before in chapter 5 in 212. We studied before if we are having a parabola, the length of which is L and the magnitude is A. And also if we are having half of a parabola, the value is A. And if we are having a parabolic spandrel, and this value is A. So this is parabola, this is half parabola, and this is parabolic spandrel. Okay? Now here the area is 2/3 base times height, L multiplied by A. And the position of the centroid is in the middle from symmetry. This is L over 2. And in case of half of parabola, the area is also 2/3 A times L, the same. But the position of the centroid is at a distance 3/8 of L, okay, measured from the right angle triangle here, okay? And for the parabolic spandrel, what's the meaning of a parabolic spandrel? It means that this is a parabola and the tangent of the parabola is asymptotic here. So this point is called the vertex. Okay? And in this case, the area is AL over 3, and the position of the centroid is at a distance L over 4. Take care that if I gave you, for example, one of the bending moment diagrams looking like this, and I told you that there is a parabola here, and its value, for example, is A, and the magnitude of this diagram is B. We notice that this is not a parabolic spandrel because the tangent of the parabola is not horizontal. So I'm going to split this, I'm going to decompose this diagram into a triangle with magnitude B and superimposed on it a parabola with magnitude A. I cannot say that the area of this diagram is B multiplied by L over 3. This rule is valid only if the tangent to the parabola is horizontal. So this is the vertex. Therefore, this is a parabolic spandrel, and I can apply this rule, and I can apply this rule for the location of the centroid. But if it is not tangent, it means that the magnitude of the shear at this point is not 0. Then in this case, I will have to decompose the diagram treat the parabola alone and the triangle alone. Okay? Now let us have applications for this. Let us have an example. It is required to find integral m1 m naught dl over ei for the shown cases. This is a diagram, a positive diagram. Its magnitude is a. This is m naught. And the length here is L. And the corresponding diagram is negative, and this is B, and this is M1. And another case where I'm having half of a parabola. This is L, and this is positive, and corresponding to a positive diagram like that. This is M naught and this is M1. Let us solve these two cases. Okay. Here I would say integral M1 M naught dl over EI equals. As long as this is of the second degree, I will start by the area of this diagram, which is 2/3 base times height, 2/3 A times L. And then the centroid is in the middle. So I am going to get the corresponding ordinate for the other diagram. This distance is L over 2. So this distance over this distance is half, which means that this value is B over 2 times B over 2. But take care, you have to put here a negative sign because this is a positive diagram and this is a negative diagram. Okay, what will be the magnitude of the integral in this case? Okay. The area of this diagram again is 2/3 base times height. So this is 2/3 base times height. The centroid is at a distance of 3/8 of L. So I want to get the corresponding ordinate. Okay? So I'm going to say 3/8 of L over L is equal to this value over this value, which means that this value is 3/8 of B, which means that this is A BL over 4. Okay? Of course, this is positive and this is positive, yet the result is positive. Again, if we are having, for example, a diagram like this, and this is A, and this is B, this is negative, and this is negative, and this is C. This is M naught diagram, and this is M1 diagram. Take care, this is not a parabolic spandrel. Why? Because when you look to the tangent, here, the tangent is not horizontal. This case is happening when the shear value at the end is not 0. So this means that the slope is having a certain value, and it will be it can be thought of a triangle and added to it a parabola like that of magnitude A. Okay. So we are going to consider that M naught is composed of two diagrams, this triangle, and added to it the parabola instead of having this shape all at once. Okay? So we are going to say here that the integral will be equal to, I need to integrate this triangle on this triangle. Both are negative, يبقى the result will be positive. I can take the area of this one first, which is B L over 2. Where is the centroid of this diagram? The centroid is here at a distance of L over 3. So we get the respective ordinate. L over 3 over L should be equal to this value over C. يبقى this value is C over 3. يبقى we multiply the area of this triangle multiplied by the respective ordinate. But what is the other component of M naught diagram? It is the parabola. Because if you added the parabola to this triangle, you are going to get the original shape that is given to us. يبقى now the parabola is positive and the triangle is negative, يبقى you need to subtract. This is negative. The area of the parabola is 2/3 A multiplied by L, and the centroid is found in the middle. You need to get the respective ordinate. Because it is in the middle, this value is C over 2. Okay? So this means that this is BLC over 6 minus ALC over 3. Okay, this is the result of integration. Time. Let us have another case. What if we are having a parabolic spandrel integrated on a trapezium? Another example. For example, we are having a parabolic spandrel here. How did I know that this is a parabolic spandrel? Because the tangent is horizontal. This value is A. I wouldn't care about this value because I'm not going to use it. I'm going to use the parabolic spandrel as one shape immediately because I know the area and I know the location of the centroid. And here we are having the respective diagram is something like this. This is C and this is D. Okay, and also it is a negative diagram. Okay. So if I want to get integral M1 M naught dl over EI, I would say this is a negative diagram integrated on a negative diagram. The result is positive. I will start with the area of that one. The area is AL over 3. Of course, this distance here is L. Okay? So this is AL over 3. Where is the centroid? If you recall, the centroid will be at a distance of L over 4. So I want to get this respective ordinate. How can I do this? If you take a line here, this value is C, and this value must be D minus C. So this ordinate here will be this small magnitude, and we can get this by similarity. We can say that L over 4 over L is equal to this part over D minus C. So this should be D minus C over 4. And the remaining portion is C, which is that one. Therefore, I will multiply here. This is multiplied by, this ordinate is C plus D minus C over 4. Okay? By this way, we can determine the integration easily. Now let us move to some problems. I will start by a simple problem. Example 1. find uy at point B. Now we are having here a cantilevered beam with a distributed load W. This is point A and this is point B, and this is the span L. We know that the deflection of this beam will look like that. This is Uy. We need to determine the deflection at point B. So I will get here the reaction. The support reaction is WL, and the moment reaction is WL square over 2. So if you draw the shear, the reaction is on my left hand side and upwards. It will be positive WL, and the shear here is equal to 0. Therefore I will connect them with a straight line like this. This is Q naught. So what will be the bending moment? The bending moment at point A is negative WL square over 2, drawn above the datum, and the bending moment here is 0. We connect these two by a straight line, and then we suspend a parabola. The magnitude of the parabola is WL square over 8. But take care, because the magnitude of the shear here is 0, the tangent to the bending moment is horizontal, so this is a parabolic spandrel. I don't need to divide this into a triangle and superimposed on it a parabola. I can take this as one shape, which is a parabolic spandrel, and it is a negative diagram. So this is M naught. So for M1, I will have to apply the unit load at point B, and I will remove everything, all of the other loads. So the reaction here is 1, and the bending moment is 1 by L, which is L. The corresponding bending moment diagram is L, and this is negative like that, and this is M1 diagram. Since this is of the second degree and this is linear, we have to start by getting the area of that one and the corresponding ordinate from here. So I'm going to say that 1 multiplied by Uy is equal to integral M1 M naught dl over EI. And this is equal to, I will take 1 over EI as a common factor, and I will come here to the area of the parabolic spandrel is 1/3 base times height, which is WL square over 2 multiplied by L over 3. This is the area of the parabolic spandrel. The corresponding ordinate here, the centroid is at a distance of L over 4. Okay, so this means that this is L over 4 and this is 3L over 4. So from similarity, you see that this distance over this distance is equal to the ordinate over L. This must be 3L over 4. Okay? This is multiplied by 3L over 4. If you did that, this will be WL to the 4th over 8 EI. This is the vertical deflection at point B. Of course, we solved this problem by symbols. We did not substitute numbers because it is a very simple problem. Now let us have a little bit harder one. So example number 2, find the vertical deflection at point C. Now we are having a beam like this, and here we are having a distributed load and a concentrated load. This is 10 kilonewton and this is 8 kilonewton per meter. We are having these distances. This is 2, 3, and 4. This is point A, B, C, and D. Again, we say that the deflection at point C is equal to integral M1 M naught dl over EI. So I will have to draw the bending moment diagram due to the applied loads, due to the main system, and then I'm going to put a unit load at point C and draw the bending moment M1 due to the unit load. Therefore, I will come here, and first of all, we have to get the reactions. We are going to get moments above this point. So the reaction will be 22 kilonewton. From sigma Fy is equal to 0, this will be 16 kilonewton. Okay? And then we are going to plot the bending moment. Take care of the steps. Now, this is M naught. The moment here is equal to 0. If we take a section like that, the moment at the end is equal to 0. The moment at point B, this load is rotating this way. So the tail of the arrow is above the datum. So I'm going to have, this is 20 meter ton. And the moment here is 0. We are going to connect them with a straight line. Why a straight line? Because we don't have any loads applied between points A and B. This will look like that. And then we take moments about point C, the 22 times 3 minus 10 multiplied by 5, it will give us here 16 kilonewton meter, and this will be the magnitude of the bending moment like that. Now we know that the bending moment at point D is equal to 0, so we are going to connect this like this, and we are having a distributed load. So we are going to suspend here a parabola. The magnitude of the parabola is 4 square multiplied by 8 over 8, which is 16 as well. Now we are having, this is the shape of the bending moment M naught. Take care. Now we can live with this shape, but maybe we want to simplify a little bit this part. Because if we leave it this way, we have to get this point by similarity, and we have to get the area of this portion and the area of this portion and the location of the centroid of each part. You can decompose this and you can draw the bending moment. This is 20 negative, and here this is 16, this is negative, and this is positive, and then this is a triangle positive, and superimposed on it a parabola like that, and this is 16. This is M naught. Okay? Now take care that when you, either that you can take these two triangles as this shape, or you can take two triangles this way. The superposition of these two triangles will result in that one exactly. But this one is very easy in the integration process. Now, if I want to get the deflection at point C, I will locate a unit load here. So I will put here a unit load. This is 1, and this distance is 3, 2, and 4. I will get the reaction by taking moments about this point, And finally, I can draw the bending moment diagram. The bending moment diagram will look like this. If you get this reaction multiplied by the distance 3, the moment diagram here will be 1.714, and it is positive. So this is M naught. It is better to locate M1 under M naught exactly to perform the integration easily. Okay, this magnitude here is 1.714, and this is positive, and this is positive. This is M1 diagram. This part is 0. What am I going to do in order to get the deflection at point C? We have to integrate M1 and M naught. We are integrating this triangle on nothing. It gives us 0. We have to integrate the upper triangle on this triangle, and then add to it the lower triangle on this triangle, and then this triangle on this triangle, and then the parabola on this triangle. So we are having 4 components. So finally we can say that, let me erase this here please. We can say that Uy equals 1 over EI into, take care, I want you to answer the way I'm writing down here for you. I am not calculating these numbers by the calculator and write the result here immediately. But rather I'm going to show the steps, because if I did any mistake in the calculator, yet you can get most of the grades. So here I will say the area of this triangle is 20 by 3 over 2. I am integrating a negative on a positive, the result will be negative. So this is 20 by 3 over 2 times the respective ordinate. The respective ordinate, the centroid is here. When you go to this distance here, you know that this is L over 3. Therefore this part will be 1.714 over 3. This is 1.714 over 3. Then we are going to integrate the triangle on the triangle. The area of this triangle, both of them is positive. The result is positive. 16 times 3 over 2 multiplied by the centroid of this triangle is here this time. So you want to get the respective ordinate. This distance here is 2/3 of L. Therefore you say that this distance over this distance is equal to the ordinate over 1.714. This value should be 1.714 times 2 over 3. Therefore this will be 2 over 3 times 1.714. Okay? Then we are integrating the triangle on the triangle. The area of the other triangle here, this is plus 16 times 4 over 2 multiplied by the centroid is here, so the respective ordinate, again the respective ordinate will be 2/3 of 1.714. Okay? Because that this distance is 2 over 3 and this distance is 1. Okay, so 2 over 3 over 1 should be equal to this value over 1.714. The corresponding ordinate is 2/3 1.714. So this is 2/3 of 1.714. There remains the parabola. The area of the parabola is 2/3 base times height, and the centroid of the parabola in the middle. So we are getting the corresponding ordinate, which is half 1.714. So this is plus 2/3 16 by 4 multiplied by 1.714 over 2. Again, how did we get that? The area of the parabola. This is the area of the parabola, which is 2/3 base times height. The height is 16 and the base is 4. And the centroid is in the middle. So this value should be the middle or half the value of 1.714. If you did this calculation, this will be 83.4 over EI. It means that if we recall the method that we studied in chapter 3, this part of the deflected shape is hugging, and the deflection here should be equal to 0 because the bending moment is a negative moment, and from the inflection point to this point the deflected shape is sagging, so it has to change like this. Okay, this is the deflected shape. Now we knew the exact magnitude of deflection here. This is 83.4 over EI. So not only that we determined the shape of the deflection like in chapter 3, but also we got the magnitude of the deflection at a specific point. We wanted to get the deflection at point C, so we drew the bending moment and then we simplified the bending moment. We removed all the loads and we put a unit load in the direction of the desired deflection, and we drew the bending moment caused by that, which is the M1 diagram, and then we integrated M0 and M1 diagram, and we got the result. What is the meaning that the result is positive? It means that the deflection here is in the same direction of the assumed unit load, and as long as you assumed it correctly downwards, the result was positive. Okay? Then you should be able at this stage to solve the assignments on the deflection of trusses and beams. I will be solving more problems for you as a matter of practice, and afterwards we are going to go into the reinforced concrete part of the course. Thank you very much.